Hello friends, this video on Chemical Kinetics part 21 is brought to you by examfear.com. No more fear from exam. Now we'll talk about a very critical topic called temperature dependency of rate constant. As you see, the tomato or any vegetable spoils faster in warm weather. The temperature is more, the reaction rate is more. This is what we have seen, right? Temperature is directly proportional to rate of reaction. High temperature at warm weather, in warm weather temperature, the tomato spoils faster. That's why this refrigerator has been created, because in refrigerator the temperature is low. So the fruits and vegetables in the refrigerator they don't spoil faster. The reaction rate inside the products which we keep in refrigerator is slower, right? Because the temperature is low. Also we have discussed about this, we lose a lot of weight during fever because during fever the body temperature is more, the reaction rate is more, and we lose fats. So we have seen this in our day-to-day life, right? The temperature has a huge dependency on rate constant. And most of the chemical reactions you see are accelerated by increasing temperature. Correct? For example, if you see decomposition of N2O5, decomposition if you want to break this. Now if you see the T half for this reaction will be 12 minutes at 50 degrees Celsius. For the same reaction, T half becomes 5 hours. It will take 5 hours to decompose to half at lower temperature, that is 25 degrees Celsius. You lower the temperature all the more at 0 degrees Celsius, the T half becomes 10 days. The same reaction took 10 days for concentration to become half at 0 degrees Celsius, and the same reaction took only 12 minutes at 50 degrees Celsius. So the increase in temperature, increase in rate of reaction. Correct? Also, if you see the mixture of KMnO4 and oxalic acid, so KMnO4 will decolorize faster at higher temperature. If you have this KMnO4, potassium permanganate and oxalic acid, this mixture, KMnO4 will lose its color or decolorize faster at higher temperature. It has been found that, actually I have told this also, for a given chemical reaction, for every 10 degrees Celsius rise in temperature, the rate constant is double. For every 10 degrees Celsius increase in temperature, the rate constant is almost double. We will understand this in more details now. One more good example for this is magnesium and oxygen. They react very slowly at room temperature. This is my room temperature. They react, but the reaction is very slow. But the moment you increase the temperature, you're not even burning it. If you see it's in a beaker, you're not burning it actually. Increase the temperature, it burns actually. You're not directly burning the magnesium. You have kept in a beaker and you're just heating the beaker, making it a little warm. The moment you heat it a little bit, it burns. The same magnesium, but the reaction rate is different, right? And this temperature dependent rate of chemical reaction, it was proposed by a Dutch chemist Van Hoff in 1884. In 1884 he proposed this, that the chemical reaction has a huge dependency on temperature, right? And he gave a little bit of, he gave an equation also, but he was not able to explain this properly, why it is having, right? He was not able to provide the physical justification or interpretation for this observation, but he observed that chemical reaction depends on temperature in 1884. Then in 1889, this guy Arrhenius, the Swedish chemist, he provided the physical justification and interpretation of temperature dependency on the rate. He gave a law, he gave an equation actually, K is A e to the power minus A by RT. This is called Arrhenius equation, where this K is my rate constant we have studied. The same Rate is nothing but Ka to the power x b to the power y, right? The same K is here. This is the same K. A is called pre-exponential factor. It has various names. It is called pre-exponential factor. It is also called Arrhenius factor. It is also called frequency factor. There are so many names for this. And please note, it is a constant value. A is a constant value for a given reaction. For example, if you talk about H2 plus O2 is water, this will have a constant value of A. You talk about any other reaction, C plus O2 gives CO2. This will have a constant value of A. So A will be specific to reaction, right? EA is the activation energy, and thus EA is the activation energy. We'll study about activation energy in the next slide. Activation energy, and the unit of activation energy is joules per mole. That is the activation energy. And T is my temperature, and please note it is in Kelvin. In most of the chemical equation we use temperature in Kelvin. Here also we are using in Kelvin. And R is my universal gas constant. Right. So K is equal to A e to the power minus EA by RT. That is the formula he prescribed. Here a new term, activation energy, has come, so we'll talk about activation energy. Before we study activation energy, let's know the fact that this Arrhenius equation which we just saw, right, that is my K is equal to A e to the power minus EA by RT. So there are so many justifications to this, and as I told, in 1884 Van 't Hoff proposed this, but he was not able to give a justification. So in 1889 one justification was given by the Arrhenius, and he used the concept of activation energy to prove this. Another justification was given by collision theory, and another justification was given by transition state theory. So in this chapter we'll understand Arrhenius concept of activation theory and collision theory to understand this equation, why this equation came, right? This was the experimental equation, actually based on the experimental data he came up with this equation. But why this equation comes, to understand this equation there were so many theories proposed, right? So K is equal to A e to the power minus EA by RT. This is an experimental equation. Based on experiments, this equation has been found. But why this equation is correct, there has to be a justification, right? We need to understand why this is coming, why we have this EA, why we have R, why we have T, why we have A, right? So those justifications were given by three different theories. First was the Arrhenius, he gave this explanation in 1889. We'll understand that. Then there was a collision theory proposed later. We'll understand that. And there was a transition state theory also proposed. We'll not understand that. We'll understand only these two theories, right? Since the Arrhenius concept of activation energy is totally dependent on activation energy concept, let's understand the activation energy concept. Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again.